on the website, and they ask opinions, and the surveys that you see on a website will only be people who visit that website, right? So if you visit some political party's website and they ask, and they have a survey on it, and it's overwhelmingly feeling one way or another, it's not an accurate picture of America, right? So if you go to if you read the comments section on, say, Fox News or something, okay, read comments on news articles on Fox News, it's not going to be an accurate representation of the United States as a whole versus, or if you go to YouTube, it's also not going to be an accurate representation of what people are like. So it's, yeah. If it just says focus group, probably and they don't say how they gathered their focus group, you probably cannot draw anything meaningful from it, okay? But if the focus group was done in a decent fashion, or if they say something, then more can be said. I don't know, has anyone heard of the blog 538? 538? It's on the New York Times. This guy Nate Silver, he does all this studies. A lot of good insight on political polls and how different organizations will be a little bit biased in things, and so how he kind of weights that against his predictions. And so he makes predictions about the election, and I don't know, some interesting insights there. So it's a political page. 538, based on the number of electoral votes in the electoral college. So, all right, so let's just talk about describing data. Okay, so this is going into chapter 2. The class might end before I get onto the topic of standard deviation. I've recorded a video defining standard deviation, and so that will be part of your homework to watch that video and learn about standard deviation. But I'll at least talk about it. Okay, so when we gather data, we gather information in variables. So data can be thought of as just organized information, okay, or just gathered information, and generally organized. Okay, so data is collected information. Organized. And we might collect when we create a data table, we might have person 1, person 2, and we might collect their height, weight, gender, etc. Okay, and person 1 might be 5'5" and weigh 105 pounds, and is female. Person 2 might be 5'10", weigh 165, and is male. Okay, this is and so on and so forth. Okay, and so we look at the variables. These are the bits of information. This is the what in our data set. Pieces of information we collect. And we have two types of variables, okay, or two large types of variables. Okay, and we've got so we have quantitative or numeric variables. And we have categorical variables. So numeric variables measure quantity, or quantitative variables measure, they answer the question how many or how much. Okay? So it gives us, tells us how many or how much. And within quantitative variables, we have continuous variables and discrete variables. Versus discrete. Okay. Continuous means it can take on any value in a certain continuum, and discrete means it only takes on certain values. So we asked the number of children a person has had. Okay, so number of children born to a person, that's going to be discrete. You either have 0 kids, 1 kid, 2 kids, or some whole number answer of kids. Okay. Continuous, on the other hand, could be something like your height. Okay, you could be 5'9". You could be 5 foot 9.1 inches, 5 foot 9.234 inches. Okay, it's really just the measurement of height is just limited by the accuracy of our means of measuring our tools here. Okay, same with weight. Weight would be continuous, but you know, how many eyes you have, that would be discrete. Okay, how many number of legs, number of feet, discrete. Okay, categorical, on the other hand, does not tell us how many or how much, but tells us what type. What type? Okay, it tells us. Most categorical variables are nominal, meaning we just assign a name. So male, female, that would be a categorical variable. It tells you you are either male or female. But some categorical variables have a natural order to them. Okay, so we have nominal. These are just basically labels. And then we also have ordinal. There's a natural order. So what t-shirt size do you buy? That would be a categorical variable. Small, medium, large, extra large. But there's a natural order. It makes sense to say small, to put them in an order, right? Small, medium, large. And we can make comparisons and saying, okay, well, large was bigger than medium, and medium is bigger than small, so that implies large is bigger than small. Okay, so we can do that with ordinal variables. Some variables, there's a bit of a graying line. We're not entirely, and so anytime you try to split things into distinct categories, there's always just there's a bit of gray. So I don't know. So if you went to Amazon and you look at customer reviews, is the star rating, is that categorical or quantitative? Categorical. It's a little tough to say. It's a little tough to say. Okay. It might seem like it's ordinal, 1, 2, 3, 4, 5 stars, but it also tells us how many stars somebody gave to a product. Okay. So, or what about shoe size? Right. Your shoe size. Quantitative, discrete, maybe. I don't know. You wear a size 8.5 or a size 9 shoe, but it doesn't make sense to say someone with a size 13 shoe has feet that are twice as big as a size 6.5 shoe. Or, well, actually, in that example, it might actually work out to be twice as big, but it doesn't. Okay, and some things, just because a number shows up doesn't mean it's numeric. So if I ask you, what's your area code? area code is not numeric or quantitative, it's a categorical variable. Okay? It doesn't, anytime you have a numeric variable or quantitative variable, it makes sense to take differences or averages, but it doesn't make sense to take averages of area codes or differences between area codes, right? Your area code is 310, your area code is 213. You have 80 more area code points. It doesn't work. So we have that. When you have a table of data like this, each row is an observational unit, okay? So then, so once you've gathered data, sometimes we want to summarize the data, either with a table or graphically. So, summarizing and displaying data. Okay, so let's say, I don't know, let's say we went around the classroom and you guys, for whatever reason, shared all of this information with me, okay, your height and weight, and I don't know, there's 30 something of you, okay, so we finally go through our entire list, person 30, let's say 35, and you know, we created a list of male and female, and we've generated or gathered all of this data, okay. And so to summarize this, when we have categorical data, we can create something called a frequency table. Okay, and so the only categorical variable that we have here would be gender, and so we can create a frequency table for gender. Very simple. We would say gender, and then we'll list off the frequency, and we list off the genders. We have male and female, and here, okay, and so maybe we've gone through and we counted up and we said, oh, okay, well, there's 35 people total, 10 of you are male and 25 of you are female. And so this is my frequency table. And we can go through and we say we can create a bar chart. Create one column for male and a bar for female, and okay, and so it's good to label your scales, and so this bar goes up to bar 10, and this bar goes up to 25. And that's that, okay? It's very simple. I don't think this will give you any problems. Okay? But that's a bar chart, and that's we use this for categorical data, okay? And then sometimes you'll see pie charts, like PowerPoint loves to create pie charts, but we generally don't like pie charts. Okay, and the reason for my dislike of pie charts is that our eyes are very bad at distinguishing. Alright, so this is an aside. You don't have to draw this, but if there were 3 categories and they looked like like this, okay, and you had 3 bars like this on a piece of paper, you would probably be able to order them, first, second, and third, okay, in terms of height. Your eyes are very good at distinguishing which one's the tallest and which one's not. But then if you see something like this, which one's the biggest and which one's the smallest? Your eyes cannot do this. So. On the other hand, we have quantitative data, or numeric data. And there's all sorts of things that we can create. And we're going to show you the dot plot and the histogram. And the book used to teach stem plot, which we don't really do anymore. Okay, so a dot plot puts a dot for every at every value we observe. Okay, and so I got rid of our set of data. But let's say we listed off person 1, person 2, person 3, all the way up. Let's just say we look at the first 4 people and their weights. And let's say it was 110 and 150 and 125 and 170. Okay. Okay, so you would draw a dot at for every point that we had. So we had 120, 150, 125, and 170. Okay, this is just a very crude dot plot where we only have 4 data points. Okay, both dot plots and histograms they really show their power when you've got a lot more data to look at, and not just for individuals. Okay, because what we'll talk about here in a moment is the shape of the graph. So if we looked at the weights of people, you'd probably see a dot plot. All of these dots are supposed to be okay, you might see something like this. Okay, and this would be a dot plot with more dots. Okay, and this could be weight, and you could just imagine having a longer list of people. Okay, and so for every person you get a dot, and so if we had however many, if there's 25 dots here, that means our data set had 25 individuals. Okay. And so this would be a dot plot, and we can talk about the shape of the dot plot, looking something like that. A histogram is very similar, except rather than drawing dots, we use bars. Okay, and it looks a lot like a bar chart, except in a bar chart we've got a space between the different bars, and with a histogram there's no space. There's a break like that in the data. So this would be called a histogram. And so the way a histogram would work is similar to a dot plot, except in the histogram we take our numeric data and we build up categories. And we say, All right, we're going to create a bin. And we're going to say, we're going to count everybody who weighs between 100 and 119 pounds, everyone who weighs between 120 and 139, 140 and 159, and we get a count, so on and so forth, of however many people fit into this this range or this category. Okay, so maybe 4 people fit in this range, and 8 people fit in that range, and 9 people in this range, and we draw our bars according to the bins there. Okay, now these are not. I don't have time to create a full list of data and then work through generating the histogram, but I hope the concepts behind the dot plot and the histogram are okay. Is that all right? And so if you were presented with a histogram and you were asked, you know, how many people are in this range, you should be able to provide some kind of answer. So with when we see the dot plot and we see the histogram, we can talk about the shape. Okay, so both of these, the histogram and the dot plot, they have the same shape here, and this shape So I'm going to draw some curves up here to illustrate shape, okay? But underlying the curve, you have to imagine you've got some kind of dot plot or a histogram with the underlying dots there, okay, to support this thing. Okay, so this shape we call skewed right, or right skewed, okay? And any guesses as to what we would call this shape? Yeah, left skewed or skewed left. Alright, and to help you remember which is skewed right and skewed left, to give you the slightly violent image of if you had to use this shape as a weapon, okay, which side would you use to stab someone or skewer someone? You would use the right side, and over here you'd use the left side. And I know it's a little gruesome, but now you will remember which is skewed right and which is skewed left. Okay, so that's skewed right, skewed left, and the other one is symmetric. Okay, so what does it mean if something is skewed right? If something is skewed right, it means the bulk of data points are in some region here, okay? So this probably, you know, the weights of people in general are skewed right, okay? At least weights of Americans skewed right. And what this means is that most people are in some range here, okay? And so let's say the average is right here at like 160 or something. There are people who weigh a lot more than 160, maybe someone who weighs 300 pounds or something, okay? That means this person is how much over the average? 140 pounds more than average, okay? On the other hand, if we went out the same distance, 140 pounds less than average, how much would that person weigh? 20, okay? And nobody weighs 20 pounds, okay? At least if we're talking about adults, right? There shouldn't be any adults who weigh 20 pounds. And so what skewed right indicates is that while most are in this region here, you have some people who are much higher than the average, but you have nobody who are as equally far below average. Okay. You have so skewed right. You have yes, people exist who are much higher than average. But none exist who are equally distant below average. Skewed left is would be just the opposite. Okay, so this would be like test scores or something. Okay, most people are in some region up here, you know, 70 and 100% or something like that, and you don't have anybody. You have some people who are much lower than average. Okay, but you don't have anybody who's much higher than average, just because you can't get over a certain score. Symmetric is means as you go further out, you'll have just as many people above average as you would people who are equally below average. Okay, so things like IQ is symmetric. You have some people, most people are in this average zone, but the further you go above average, you have fewer and fewer people. Okay, but you have just about as many people who are way above average as you do people who are below average, okay? or equally far below average. So you have just about as many people. So average IQ is 100. You have just about as many people who have IQs of 150 as you would people who have IQs of around 50. So that would be symmetric. There's all of these have one peak. There's descriptions for the number of peaks. And so we have, for anything with one peak is unimodal. We've got two peaks, bimodal, and then if you have more than two peaks, yeah, you could say trimodal or whatever, but we usually just say multimodal. Okay. And then if there's no peaks, something like this. This would be uniform. So one peak. This is things like IQs, bimodal. We might have this if we had measured testosterone levels in people. Okay, you'll see two peaks. You'll see a peak up here for men. This would be like the average testosterone level in men. Okay, and some men have higher levels of testosterone, and some men have lower levels of testosterone. But then, actually, testosterone will probably look a lot like this, and this would be men, and this would be women. Okay, and women have testosterone also, but in general, there's kind of like this no man's land of where you don't have people in this zone. Would either be men with very low testosterone or women with very high testosterone. That's something like that. Or vocal pitches. Okay, you'll see bimodal because again, men will create kind of this range for a vocal pitch, and women will have generally their vocal pitches are higher. Okay, but probably the peaks will not be as distant for that one. Heights, actually, the peaks end up being so close that it almost looks unimodal when it talks about height. Although some argue that it's bimodal. You have an average height for women and average height for men. That's generally the most common reason for having bimodal distributions, at least for things that we observe, is because there are differences between men and women. But then a lot of the other things are unimodal, right? Like IQs, IQ scores, unimodal, things like that. Uniform, this would be like, what's the last digit of your telephone number, okay? We probably have just as many people whose last digit is the number 1 as we have people whose last digit is the number 8 in general, okay? And so here there's no real standout in terms of which number is a lot more common than other people's numbers. So we have summaries, okay. So we have to talk about the mean and the median. So we've got notions of center. Okay, so when you're going to describe a set of data, you want to talk about where the center of the data lies. Okay, what is quote the average? And so we've got we have two notions of center. One is the median. The other is the mean. The median is the point where half of your data is larger than the median and half are smaller than the median. I think you guys are familiar with the median and the mean. Okay, and then the mean is you add up all of the numbers and you divide by how many numbers you have. The mean is also can be thought of as the balancing point of the data. So the mean helps us. I don't know. It's a good visual way of visualizing it and eyeballing where the mean may lie. And so just get a set of data. Okay, so this is a set of data, and this is radish growth and light. Okay, so what we did was we set some radish seedlings in some dirt, and then we exposed them to light, and then we just measured how much did these radishes grow. And so these were the numbers in I guess I don't know, millimeters or centimeters, whatever. These were the numbers that we measured. So, the median, to find the median, we just have to find the point where half are smaller and half are larger, okay? And so what this involves is we've got to arrange them from smallest to largest, which we've already done, okay? But step one in finding the median, arrange the numbers from smallest to largest. Find the number in the middle, okay? I don't know, maybe when you were in junior high they said, you know, start out here and then work your way in. That works, but if it's a large data set, it might be a little cumbersome, so I say find the number in the n plus 1 divided by 2th position. Where n is how many numbers you have. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. I have 14 numbers. So in this case, my n is equal to 14. So my n plus 1 over 2 would be 15 over 2, 7.5. I would find the 7.5 number. My median is not 7.5, but my median is this number in the 7.5 position. Okay, so what I mean by that is I'm going to turn across and I go 1, 2, 3, 4, 5, 6, 7. This is the 7th number, and over here is the 8th number. So the 7.5 number is between the 7th and 8th number. And so I would take the average of the 7th and 8th number, okay? So I would say the 7.5 number is the average or the mean of the 7th and 8th number, okay? So of 9 and 10. So I would do 9 plus 10 is equal to 19 divided by 2, 9.5. Okay, so my median is equal to 9.5. Alright. The mean, on the other hand, we would take all of these numbers, add them up, and divide by 14. I've got 14 numbers, so actually I'm going to have to do this. I don't know what this number is going to be. Okay, so I do 3 plus 5 plus 5 plus 7 plus 7 plus 8 plus 9 plus 10 plus 14 plus 20 plus 21. And I divide by 14, and my mean is 9.93. Okay, so my median and my mean aren't exactly the same. Is that okay? Yeah, that's okay. All right. These are again notions of center, and so I can kind of illustrate the idea of mean and the median. Maybe with draw a dot plot here. So let's make a dot plot. Let's see. 0. Alright, so these are supposed to be approximately equally spaced out. And so this is 1, 2, 3. I'm going to draw a dot at 3, a dot at 5, 7, 7, 8, 9. Okay, so this is our dot plot with all of these things, and you can imagine if this were a seesaw, okay, and these were all like bricks of equal weight. Where would I put the little fulcrum, the little triangle, so that the seesaw stays in balance? Okay, where I would put it would be right here at 9.93. This point right here, 9.93, serves as the mean, and this is where the seesaw would be in balance. Okay. And then the median is this line right here, which represents the point where half of our data is below and half our data is above. So this here is the median. We got 7 below and 7 above. Okay, symbolically for the mean, we write y bar. This represents this is the symbol for sample mean. Okay, meaning anytime we gather data, it's almost always going to be a sample, right? It's not coming from the population. The population would be everybody. So this is a sample of 14 data points. This is we put 14 radish seedlings and we measured how much they grew. And so our y bar, our sample mean, is we added up each individual y. And so you'll see y sub I representing each value of y divided by n. Okay? This here represents sum. So this is just symbolically, this is the formula for the mean, but it's just symbolically what we already know what the mean is, which is add up all the numbers, divide by how many numbers you have. Here we have the mean is larger than the median. In general, what this means is that you have outliers. The mean is influenced by outliers. So if I had changed, if the largest number is not 21, but was 50 or something, right? So if we had some super radish that grew 50 versus the other ones, the next closest one being 20 and most of the rest growing somewhere around 10, okay? That dot would be way out here, okay? What would happen to the mean? It would move. It would move in this direction, okay? In order for the seesaw to stay balanced, it's like someone's moving very close to the end, you know, the seesaw would, the balance would have to move to the right, okay? The mean is affected by the outliers, okay? What happens to the median? Nothing. The median stays in the same place. It's still the point where half the numbers are bigger and half the numbers are smaller. It's still 9.5. Okay. So the mean is influenced by outliers. The median is not. Okay, mean is the balancing point. Median is just the middle number. Whenever your mean is larger than the median, it generally means you have outliers or numbers significantly larger than the rest. Okay, so if your mean is larger than the median, you generally have outliers that are larger than the rest of the data. And if the mean is smaller than the median, generally you have outliers that are smaller than the rest of the data. In general, that's what it means. Okay, so mean larger than median, outliers in that direction, or at least your data is right skewed. Okay, so mean is greater than the median. Okay, your data is generally right skewed. Or you have outliers much larger than the rest. And then the opposite, the flip side, applies for when the mean is smaller than the median. Okay. The reverse applies. And it's all because of that notion that the mean serves as a balancing point. Is that all right with everyone? Yes, we have a question.
Yeah, does that say a sum of y(i) or 1?
Y sub I.
That's an initial?
The subscript represents each value of y. So there's a notation, but basically just add up all of the y's. So here it means technically the notation would be from I equals 1 to 14, meaning you do it from the first number to the 14th number. Add each of them up, okay? But I don't want to worry too much about it. Another question, yes?
If you just have one outlier and let's say it's really, really high, is your data still right skewed, or is the outlier showing
It's a debatable topic, okay? Skewed is...
It's like trending, so you can't just do one value.
Some would say one value would cause it to be skewed. Others would say no. It's a subjective thing, right?
One more question. The flip implies when the mean is less than median. Does it mean they are less skewed?
Yes, that's what I mean. Sorry, I didn't write it fully out, but that is what I mean. If the mean is less than the median, then it's less skewed, or you have outliers smaller than the rest of the data. So let me just leave this here. Sometimes so let's still look at this data set, our median here. Okay, and we talked about dot plots, and we could make a histogram if we wanted to. Another way of summarizing our data is drawing something called a box plot. Okay, and the book calls it a modified box plot, and they have two terms for box plot. They've got the box plot and the modified box plot. Anytime I talk about a box plot, I'm talking about what the book calls a modified box plot. Okay, so when I say box plot, I mean the modified box plot. Okay. So we'll always use a modified box plot. And a box plot is a visual tool. It's like a dot plot. It's like a histogram. Okay, meaning that it's a way to show the data graphically, but it's kind of like the bare bones, the Cliff Notes version of a set of data. Okay, it just gives you just the basics that you need to know. Okay, so it's like that. Outline or just brief flash of the data. And what a box plot looks like is there's a box, there's a line in the middle, and then lines coming off of the box, and little circles to represent outliers. Okay, so these are the parts of a box. This is the box, and the box has 3 lines. This middle one, this is the median, and this is, and I will talk about this. This is Q3. This is Q1 over there. Those are the 3 boundaries of the box. These things that come off, they're called whiskers. Okay, this is also a whisker on the lower end. And if you see circles, these are outliers. Alright, so let me just again, for the boundaries of the box, we have Q1, median, Q3. Okay, Q1 and Q3, these are known as the first and third quartiles. Whiskers, okay, whiskers extend to the largest and smallest data points within the fences. Okay, and we'll talk about what the fences are in a moment. And then anything beyond the fences are outliers. Okay, so points talk about what quartiles are. Okay. Are you guys familiar with percentiles? Percentiles. So if someone says you are in the 90th percentile, that means what? You're like if you took the SAT and said your score was in the 90th percentile, it means your SAT score was
Above average.
yeah, above average. It means your score was better than 90% of the people, okay, and 10% of the people scored better than you did, okay. So the first quartile, this is equivalent to the 25th percentile. Okay. Okay. And the third quartile would then be equal to the 75th percentile. So these are basically points where a fourth of the data is smaller and 3/4 are larger, and over here 3/4 of the data is smaller and 1/4 is larger. Okay? And so the way we find these is we first find the median, and then we split our data into two sets, and then we basically take the median of the first half, and then we take the median of the second half. And so if you take the middle point of the first half, you're going to get the quartile. And if you take the middle point of the second half, you're going to get the third quartile. Okay, so to find the quartiles, find the median. Okay. Then find the median. I'm going to call this the mini median of the lower half and the upper half lists. Lower half list and upper half list. So we'll go through this example, which is actually from the book, and I encourage you, as you guys do your reading, to follow the example and make sure all of your calculations line up with the calculations in the book. Okay, so this book has a lot of examples, which I think is a good thing as you do the reading. And rather than just passively going through the examples, I encourage you to take pen and paper and make sure you do the calculations and you understand where, when they do the examples, where they're drawing, where they're getting their numbers, why they're using certain numbers and calculations, rather than just passively reading through. Because a lot of times when you just see numbers, it's just like number, number, number. Okay, great. All right. I encourage you to do the calculations as you follow the example of the book. It'll soak in a lot better. All right. So here, this is our list. We found the median. Okay, we did n plus 1 over 2, 7.5 number. Okay. And so here, now I've split my list into the first 7, the lower 7, and then the upper 7. Okay. And so now I'm going to find the median of these 7 numbers. So I've got 7 numbers, so I would go to the n plus 1 over 2, so I go 8 over 2, the fourth number. So I go 1, 2, 3, 4. This number here, this is my fourth number. This is going to represent Q1. Okay, so here it wasn't like the 4.5 number, so it's not some made-up number in between 7 and 7. It's actually the fourth number itself, which is 7. Okay, I would do the same thing over here. I've got 7 numbers, so my middle number is also going to be the fourth number. If I do 7 plus 1 over 2, so 1, 2, 3, 4. My Q3 is going to be 10. Is that all right? Okay. So that gives us the box. So our box has Q1 equal to 7, the median equal to 9.5, and Q3 equal to 10. So now we've got to figure out our whiskers and outliers, okay? And so we talked about the fences, okay? So what the fences are, we've got a lower fence and an upper fence. The lower fence is equal to Q1 minus 1.5 times what we call the IQR. The IQR is just a fancy way of saying the distance between Q3 and Q1. The IQR is the distance from Q1 to Q3. Okay? Or basically just what is the difference? Q3 minus Q1, so IQR is equal to Q3 minus Q1. So my IQR here is what? 3. Okay? The interquartile range is what IQR stands for. Just sounds fancier than it is. In our case, 3. So my lower fence is equal to 7. Q1 is 7 minus 1.5 times the IQR, which is 3. So I get 7 minus 4.5. This gives me 2.5. My lower fence is 2.5. The upper fence is Q3 plus 1.5 times the IQR. So this would be 10 plus 1.5 times 3. 10 plus 4.5. 14.5. So that's my upper fence and my lower fence. Okay. And so my whiskers extend to the largest and smallest data points within the fences. So what does that mean? What is the smallest data point that I have? 3. Is it within the fence? So my fences go from 2.5 to 14.5. Is 3 inside that range? Yes. So my whisker would go down to 3. What about on this side? How far does my whisker go? It goes to 14. This is the largest data point that I have that's still inside the fence. So my other whisker goes to 14, which means 20 and 21 are then outliers, any points outside of the fence. Okay? So whiskers go to 3 and 14, and then outliers are 20 and 21. So if I draw this. So I'll draw my box, 7, 9.5, and 10. 5, 6. So one box there, 10, and my vertical bar is right there. This is my box. My whiskers go down to 3 and 14, right there. And then I've got outliers at 20 and 21. 20 and 21. And there's my box plots. Okay, this is kind of our flash summary of the data that we collected. It gives you an idea of, this gives you, the width of the box here, this is the IQR. The IQR shows you where the middle 50% of your data lie. Okay? At distance. This is 7 to 10. That's the width of the box. That's the IQR. So this gives you an idea. This is where the middle 50% are. Okay, so when we looked at all the radishes, half of the radishes grew between 7 to 10 millimeters or however much they were.
Do we have outliers on the left side or not?
We don't have any outliers on the left side, okay? The smallest data point that we collected was 3. And according to our rules on what outliers were, 3 is not an outlier, okay? If we had a data point that was like 1, a radish only grew 1 millimeter or something, that would be an outlier. That would be represented here as a dot, okay? But over here, no outliers on the left-hand side. Yes. Yeah, question?
So upper fence and lower fence aren't represented on the chart.
Yeah, we don't actually draw them.
We use them to find the
box
whiskers.
Box plot, yeah. But or, yes.
Where did you get the 1.5? Is that just the formula?
Yeah, that's just
The
the
standard,
formula. It's
okay.
a standard. It's always going to be 1.5 times the IQR more than Q3 and 1.5 times the IQR less than Q1. Okay, so remember this represents Q1. So if I take this box and I multiply it by 1.5, that takes me to where the this lower fence is, right? I take the width of the box, 1.5 times it. So I start at this end, and if I take another box and I 1.5 it, it takes me over here. And I take this box 1, and then half the box, it takes me to the upper fence on this side. 14. Oh. Okay. All right. Is that okay? All right. So the next thing, and I'm not going to be able to go into great detail on this, okay? And I've made a video on calculating the standard deviation, which is a measure of dispersion, okay? So one of the most important things that we'll learn in statistics is that when we gather data, okay, when we look around the world, is that everything is not the same, okay? And when we say everything is not the same, well, it's clear that everything is not the same. And so when things are not the same, when we see something that's different, we have to ask, is this thing that's different, quote, different, is it highly unusual, or is it something that just is part of the fact that people are different from one another, or that things are different, right? If you know, we could talk about like the average high and average low in Los Angeles or Santa Monica or whatever, and you know, a temperature might be different than that, and we ask, you know, was this very different or not? Okay, so for example, you guys like know Palmdale, right? It's out in the desert. Okay, so if I said temperatures in Palmdale the other day reached 100 degrees, okay, and you say, wow, that's hot, but it would not be breaking news, right? We would not see this on the news, and they would not say 100 degrees in Palmdale, oh my gosh, that's crazy, okay? But if we went to Santa Monica and I said it was 100 degrees in Santa Monica, that would be rather surprising, okay? That might actually be breaking news, all right? For it to reach 100 degrees in Santa Monica, that would be very unusual, right? And why is that? And it's because, well, Santa Monica, you'd say, it just doesn't get that hot. But on the other hand, if we go out to Palmdale and I said, oh, you know what, at night it reached 30 degrees, okay, that's below freezing. It reached 30 degrees. Again, it would not be breaking news. But if we went to Santa Monica and it reached 30 degrees in Santa Monica, it would be rather surprising, like breaking news, okay? So the thing there is that Palmdale's temperatures have great dispersion. There's a great variance, okay? There's a large range of temperatures we might see, okay? And what we'll what we'll learn is that the standard deviation for the temperatures is large. Standard deviation is just a way to say how much the temperatures differ from, I guess, each other. Okay. Meanwhile, in Santa Monica, because it's so close to the ocean, and that acts as a kind of a way to make things a lot more mellow, is that the standard deviation, or the range of temperatures observed in Santa Monica, is a lot smaller. Okay, so when we see things that are drastically different from average in Santa Monica, it's a big deal. Whereas things that are different from average in Palmdale, it has to be really, really different for us to notice and say it's a big deal. Okay, so I'm going to go a little bit over 9:30, and I apologize. So let me just throw up a few, kind of just the general idea of dispersion and measures of dispersion there. And we've already learned one, which is the IQR. The IQR is a way to measure dispersion or spread. Okay, but then we'll also learn the standard deviation. Okay, so. These give us an idea of, are they all very similar to each other? Are the numbers similar to each other, or are they very different from each other? Okay. Close together, or very different from each other. Okay, so small spread or low dispersion means the numbers are similar. Okay, and so think temperatures in Santa Monica. And large spread or high dispersion. Numbers exhibit a lot of variance. So these are temperatures in Palmdale. Okay, and so we'll have to look through, watch the video that I have on calculating the standard deviation. I hope most students are okay after watching the video, but if you've got questions, ask me, post your questions on the Facebook group, or if you don't have Facebook, you can email me. But post your questions there, and good luck with the homework. So again, what you'll do is on the web page, you'll click the XL13, and listed under homework 1, you'll see the reading that I've assigned, and then the homework problems that are assigned. Also on the homework page, I've recorded all of the answers, or I've written out the answers to the homework, okay? Please don't just watch the answers if you get stuck, okay? Really try to do the homework problems, do them yourself, go through the reading and make sure you can do them, and then consult the answers to make sure that you've done them correctly. But I offer them there as a service to you to help you learn, because I know 3 hours is a lot, so I think they are helpful, but they're there to help you. Don't use them as a crutch and hinder your own learning.